Hi everyone, welcome to this session of the MICCAI Educational Challenge 2024. My name is Sanya and I'll be walking you through this tutorial on implementing vision transformers from scratch in PyTorch using any dataset of your choice. This is the GitHub repository that contains end-to-end instructions with a Google Colab notebook attached to it. So feel free to check it out and do give it a star if you like it. So let's talk about the main implementation of Vision Transformers from scratch by hitting the link to this Colab notebook. So, Vision Transformers were primarily introduced in 2020 to present a classification approach for images. So, if you're familiar with natural language processing, you would know that transformer models are an integral part, have always been an integral part of the natural language processing world. So, essentially, they chunked down sentences into small tokens, and then those tokens were put into a transform encoder, which led to a classification head in order to perform sentiment analysis or classify feelings or sentiments attached to the sentence, attached to the tokens with respect to the different categories that are available. So vision transformers were inspired by sentence transformers, but instead of classifying text, they classify obviously images. So vision transformers present a robust approach powered by self-attention to compete with convolution neural networks, which are considered the de facto standard for image recognition tasks. So there have been several implementations of vision transformer models so far. Those incorporating Hugging Face or the Keras APIs provide easier computations, but the problems associated with these, or even the main GitHub repositories, are the lack of transparency when it comes to the code. So for engineers or for developers, they are a godsend because you could simply implement those techniques without understanding what the code structure is like by using simple inference code snippets, right? But for students who are interested in building networks like these from scratch, for academics, it will be considered a hesitative step. It would be considered a hesitant step since they won't be provided much transparency into the structure of the model. Henceforth, through this implementation, we want to implement the Vision Transformer main paper using PyTorch on any dataset of your choice to help you implement vision transformers on any dataset of your choice from scratch without knowledge of any external APIs using just PyTorch. So that is why we have created this tutorial to help students and researchers. Coming to the main architecture of vision transformers. So essentially, you'll be provided with an image, and the image shall be broken down into several non-overlapping patches with a size that would be defined in the main paper. Once you have broken your image into several patches, into several patch embeddings, you need to add positional and linear embeddings to your image patches. This is done so that, once, for example, let us believe you took a patch from here, right? You took this patch. So you will need to tell your patch that, okay, its position in this particular image was 1, 1, let's just say. It will be the first patch that will appear from the left-hand side, top corner, right? So you will need to add such positional embeddings to your images, to your patches, so that they know upon 2D image reconstruction that they have to be placed in this particular location. Otherwise, they will get lost and reconstruct a disfigured image. That is why positional embeddings are added to your patches. Now, to your patch embeddings, we also add class embeddings or class tokens in order to tell them what exactly is their class going to be. Are they images for a particular monument? Are they images against a particular, which are not a particular monument? Are they images for a particular disease? Are they images for the absence of a disease? So the exact class embeddings need to be prepended, need to be provided to your generated patch embeddings. And a patch embedding sequence is created that contains your positional as well as class embeddings. So once you have your patch embeddings created, you need to convert them from a two-dimensional space into a one-dimensional sequence. This is done because your transformer encoder only takes in inputs in the form of a one-dimensional sequence. So you convert two-dimensional image patches into a one-dimensional sequence, you put them into your transformer encoder, Your transformer encoder will ultimately lead to a classification head, which in this case is a multi-layered perceptron head, and it then provides classification examples, answers. It will tell you what class does your image actually belong to, and what is the percentage probability of it belonging to the said class. This is essentially how vision transformers work. You break down an image into patches. From all those patch embeddings, you add positional and class embeddings. You flatten them into a one-dimensional sequence, put them into a transformer encoder. From the transformer encoder, you are led to a classification head, and finally, you are yielded with classifications. This is the description of what actually happens. So firstly, the code is already implemented, so we don't have to do much. So you're going to be cloning my GitHub repository, which contains all the files that you need to know about. Then we are going to be seeding into our current working directory. Once you have done that, we'll also be installing the requirements.txt file. So the requirements.txt file essentially contains all the requirements that you need for the implementation of this code. And once you're done with that, we're all set to go. So to speed up the training process, we will now be talking about the data processing steps. And we have used the NIH malaria cell image dataset that originally contains 27,558 images divided equally into two categories. So the parasitized set of images contains 13,779 images, while the uninfected class of images also contains 13,779 images. Now, because we are training a lightweight model currently, we want to keep the number of images small. So I reduced the size of the dataset and structured it as follows. So our new malaria dataset contains 500 images randomly sampled from the NIH malaria cell image dataset. These 500 images contain 400 train images and 100 test images. Out of these 400 train images, we have 200 uninfected images and 200 infected images. Note that instead of the word parasitized, I have straight away used the word infected here in order to reduce any discrepancies that might happen for your understanding. Similarly, in the test subset of images, we have a total of 100 images, which contains 50 uninfected images and 50 infected images. This is done so as to reduce any biases that may creep in. Now we are going to be creating our data loaders. So our data loaders essentially help us to load data sets into a PyTorch model training instance. So over here, we're defining a new function, which is called create data loaders, which contains the arguments train dir, test dir, which will essentially contain the train directory and test directories. Transforms, any transformations that you want to add to your images to make them more robust to changes. For example, if you have a transform added for rotational and vertical flipping, then your model will be made susceptible to any rotational and flipping changes in the images, and it will be a lot more stronger compared to a model without transformations. Next, you have batch size, which we take to be 32 in this example, and nub workers would simply mean the number of sub-processes that are involved in the process. So now we are converting these variables simply into data sets. So we converted trained data into data sets. And finally, we are going to write data loaders for trained. We're going to be writing data loaders for the train set as well as for the test set. So we write a train data loader code, which contains the variables train, batch size, shuffle equivalent to true, nub workers, and pin memory equivalent to true. And we write a code snippet for test data loaders also, which will contain the shuffle value to be false, because in the test set, it doesn't really matter if you put shuffle to be true or false. So now we are going to be specifying our manual data transformation pipeline. We'll be adding transformations, including resizing, in order to ensure that all our images are resized to the size mentioned over here, which is 224 cross 224 for the images. We shall be converting the NumPy array into a PyTorch tensor, and we shall be providing it with random horizontal flipping and the random vertical flipping transformations in order to make our model more robust. You can add a lot of other transformations, but I've just limited it to these two mainly for the sake of simplicity. Now, once you've created your data loader, it's time to check and let's see how it's set up. So we've specified a batch size of 32, and we've created our train data loader, test data loader, which with these class names which shall be defined. So your create data loaders function has been instantiated. It contains the train date, test date, the transform, as well as the batch size arguments, and finally these are printed. So you have a torch data loader created for the train data set, you have a torch data loader created for the test data set, and you also have the class names printed as infected and uninfected, so you know that your data loader is working. Now we shall be picking up an image from the data loader, and we shall be seeing if we are getting the correct label for it. So we are essentially using the next and the iter functions. So we are essentially going to be picking up the first image from the image batch and the first corresponding label from the label batch, and then see if they are corresponding with one another. So there you can see we have this cell image and we have the label as uninfected, which is true because clearly you don't see any staining on this cell. So it's correct. Now, we are going to be creating a vision transformer network components. The best way to approach this problem, the best way to deal with this problem is to create individual network components and then put them together in the form of a big architecture. So the respective blocks that we are going to be using are the patch embedding block, a multi-head self-attention block, and MLP, a multi-layered perceptron head, as well as a transformer encoder. So the first step in the vision transformer architecture is to create the patch embedding block. So we create a patch embedding block that contains the arguments in channels, the number of color channels, the patch size, which has been defined as 16 cross 16 in the VIT base paper, and the embedding dimensions, the size of the hidden dimensions, which is equivalent to 768. This layer essentially, it patchifies your image, it breaks down your main image into patches, and then it flattens them into the one-dimensional sequence that we were talking about earlier. So first of all, we're going to be creating a patcher code, self.patcher, wherein we are going to create a network layer that contains the parameters in channels, out channels, a kernel size, a stride, as well as padding. You can refer to the mn.conf 2D PyTorch documentation in order to get more information about how to create PyTorch layers. Once you've created your code for patching things down, we specified a patch size equivalent to the kernel size. You'll now be writing the code for creating a layer to flatten the patch. So you are now specifying a flattening layer by specifying the start dim to be equivalent to 0 and end dim to be equivalent to 3. So you're flattening the feature map dimensions into a singular vector essentially. This code does not mean that the starting dimensions were 2 and the ending dimensions were 3. It means that there is a change of 3 minus to 1 dimension only when we're talking about flattening. Hence, we are creating a one-dimensional feature vector. Once we've written down the functions for these creations, we are now going to be writing the forward pass method to pass on whatever we have carried on to the next layers. So we're writing a small assertion over here in order to ensure that the image resolution, the image size is divisible by the patch size, because only then would you be able to break it down into equal sized patches, right? Once you've done that, you are creating an instance in the forward pass for patching and another instance for flattening. Once you've done that, you can go on to creating the next layer because the patch embedding layer is now done. You have successfully broken down your image into patches and passed them over into the next layer. The next layer in this case, this is just a small example to see if your patch embedding layer is working. So we've created an instance of the patch embedding layer called patchify, and we've printed out the input image shape, the output patch embedding shape, and the patch embedding shape in the format patch size, number of patches, and embedding dimensions. So you can see the input image shape is as follows. This is the current batch size of 1. The output patch embedding shape is 1, 196, and 768, which is true because this is the batch size. As I mentioned, the number of patches has been mentioned as 196, and 768 is the embedding dimension that we had originally taken it to be. Now we are going to be talking about the multi-head self-attention as well as the multi-layered perceptron blocks. So both of these blocks, as you can see from the transformer encoder architecture, are present inside the transformer encoder itself. You have a multi-head attention block as well as an MLP block. Before you are talking about any block, you need to have a normalization layer in order to ensure that all the inputs are correctly mapped, correctly annotated. So We're writing a new NN.module class for multi-head self-attention that contains the arguments embedding dimension, number of heads or the number of attention heads that are used in the attention layer, as well as attention dropout. What are attention heads? So if you're talking about a single attention head, if you're familiar with singular attention heads, let's just talk about QKV values in self-attention and what do self-attention heads essentially do. Self-attention essentially is used to capture long-range dependencies and any contextual features that are present. So if you have an X input vector, you will be provided with three weight matrices, which are adjusted as model parameters during the training process. So you can obtain the scale dot product of the input vector with these three matrices in order to get the query input sequence, the key input sequence, as well as the value input sequence. This is possible for only one self-attention head, but in the case of a multi-head self-attention, you have multiple attention heads present, which in our case is going to be 12. So the more the number of attention heads, the more features and the more dependencies you can capture, and therefore better is the performance of the model. Coming to writing code for multi-head self-attention, we talked about embedding them, we talked about the number of attention heads, and we also have the attention dropout specified. The attention dropout for this layer is considered to be 0 according to the VIT base paper. Finally, you create the normalization layer and you create the multi-head self-attention layer, and you finally write a forward method to pass the data through the layers. Coming to the next layer, we are creating another NN.module class for the MLP, the multi-layered perceptron block, which was also present in the transformer encoder. So the arguments for this layer are going to be embedding dim, MLP size, the size of the MLP block, which defaults to 3072 according to the VIT base paper table 1. And finally, you will have a dropout rate of 0.1 specified over here. Like I told you, before any major block, we have a normalization layer in order to ensure that all the values are mapped accordingly. And finally, we'll be creating your MLP layer. Now, an MLP is nothing but a classifier, right? It's a very basic artificial neural network. So we have two linear layers. We have a GLU activation function. Between these two linear layers, we always have an activation function sandwiched between linear layers. And before we begin with the second linear layer, we also have a dropout function. So the purpose of a dropout is to ensure that there is no overfitting in the model and any neurons that are not participating towards improving the output are shut off. So this is what a dropout layer essentially does. And over here, we're writing a small sequential model for multi-layered perceptron. Finally, we define your forward pass and the MLP layer is also ready. Now we are writing the code for creating your transformer encoder. So your transformer encoder will contain your MSA as well as your MLP blocks. So we've written code for integrating your multi-head self-attention as well as the MLP block into the transformer encoder structure itself. This will contain parameters from both the models because obviously it contains both of these. And we've written a forward method over here also. Now, once you've written the code for transformer encoder, you can view a summary of the model by using the Torch info library. And you can see this is what its summary looks like. So we have the transformer encoder block, you have a multi-head self-attention block inside it, and you also have a multi-layered perceptron block or the MLP block inside it. Now we shall be putting together these four network components that we talked about. We have a patch embedding layer, we have a transformer encoder that contains the MLP as well as the multi-head self-attention blocks. So creating the VIT block will be instantiating all of these hyperparameters like image size, the number of input channels as 3, the number of patch sizes to 16, the number of transformer layers as 12, the number of embedding dim set to 768, MLP size of 3072, number of heads set to 12, attention dropout set to 0, MLP dropout set to 0.1, embedding dropout set to 0.1, and the number of classes defaulting to ImageNet set to 1000. You can also change this to 2. I have not just for this case. Now we're creating an assertion to ensure that the image size is divisible by the patch size. You can calculate the number of patches. Once you calculated the number of patches, like I told you, you are now going to be creating class embeddings in order to add class tokens to tell you what class does your input image belong to. So you've created class embeddings, then you've created your positional embeddings in order to tell you where exactly is a particular patch located in your image. You're adding a dropout layer, and finally, you're creating your patch embeddings. Note that your class embeddings and positional embeddings are most often created before your patch embeddings. Now you're creating your transformer encoder, which contains your transformer, which is a sequential model that contains your transformer encoder block. You're creating a classification head, which is outside your transformer block, which is again another sequential model, could be an MLP, a single layered MLP. And finally, you're defining your forward method. You're adding your class token and prepending it to the patch embeddings. You're adding your positional embeddings to your patch embeddings. Like I said, you're concatenating everything together. So you've added all of them together. You've passed your patch, positional, and class embeddings through your transformer encoder layers, and you've initialized your index logit as 0, which was present in the classifier. So now that all of this is done, you can print your model, see if it works, if it's printing the number of class names correctly, and finally you can begin with training. In order to initialize training, first we've used a Python file known as engine.py from the PyTorch deep learning library. I've also put it down in this repository so you can straight away clone it and use it directly. So we've defined our optimizer as Adam with these parameters as mentioned in the VIT based paper. We've used the cross entropy loss function, and we're finally training our model using the engine.train method by specifying all of these parameters. So I've tried to run this using the Google Colab T4 as well as the L40 and A100 GPUs. All of them work very well, so you can use any of these. You won't encounter a runtime error in this case. So I've trained it only for 30 epochs. You can train it for more or for less according to your wishes. Once you can see model training, you can print the results, you can plot the results of your model. You can use the helper functions.py as present in the GitHub repository in order to plot your loss and accuracy curves. So you can see that our loss is receding, so it's doing quite well. The accuracy needs to be improved, obviously. Plus, you can see that our model is overfitting a little bit when it comes to the train and the test accuracies. So you can definitely learn how to fine-tune your models, but since this is a very elementary notebook, this shall not be discussed over here. And finally, we'll be using the predictions.py file over here, and you can set the custom image path and define whichever image whose predictions you would like to print. So obviously we have an uninfected image path defined over here, and the output is also uninfected, and you have a probability of 51% of it being uninfected, which is true. So our model is working. So this is all that shall be covered in this notebook. You can broaden your scope to understanding vision transformers by printing saliency maps or GradCam heat maps as are present over here. You can fine tune them, you can play around with the features a little bit and try to understand how are your models working. And I'm pretty sure this was an example that could encapsulate everything. If you have any doubts, you're free to refer to my GitHub repository, which contains almost everything you will need. And I hope this was a useful video for you. So thank you, and do let me know in case you have any doubts.